So today here to give a talk on some recent avenue on 3D printing. So normally I have been working in the topic of 3D printing since my master. So I have expertise in terms of 3D printing of metals, polymer. But during my PhD, I started working on a new domain of 3D printing, which is printing of cement-based composite material, or in civil engineering, we may call concrete 3D printing. It's a bit new topic for all of you. Though in India, we have not done in-depth research in these topics, but still many IITs and NITs, they're considering this topic as a new avenue for exploring the 3D printing in the construction industry. So basically, I'm a mechanical engineer. The point that actually motivated me to work upon this topic, like cement-based 3D printing, or you may call concrete 3D printing, is the lack of productivity in the construction sector. So here the graph that tells us that if you see the productivity of many industry, like it is completely growing over the time. But compared to that, if construction industry productivity is quite stable over the years. So these thoughts intuited me to do a bit literature review regarding the causes behind this reason. And when I was doing my PhD at Nanyang Technological University, Singapore, so our group, we have done an in-depth literature review on different causes for the lack of automation, a lack of productivity in the construction domain. And we came to a conclusion that if we can bring automation in terms of digitalizing our construction way, definitely there is some impact on the productivity of our construction sector. And when the term automation or digitalization comes into picture, we always keep a word called Industry 4.0, where we try to connect the machine with data. And in the similar line, we thought how we can bring the similar culture in the construction industry, because our construction industry is full of labor work and it is not a fully automatic process. Those who are from mechanical department, for them I made a very small slide, a schematic slide that tells us that if you want to make a concrete, it's a very simple material in the world. You have to just take cement, sand, water and stone. You can easily make concrete composite. It is a composite material. So we wanted to print such materials because of so many reasons. Why? Because if you see our construction industry, we do casting, like creating the mold box, as you can see in this picture. So once you create the mold box, then there is a process of dumping the wet concrete into the mold box. And once this concrete is completely hardened, then the mold box can be taken out to get the complete structure. So this is how traditionally the construction work takes place. But coming to printing of concrete, what is more important here, there are few reasons why I would love to print concrete instead of just casting it. The first reason, that is called design for freedom. Everyone knows that 3D printing, or you might have listened many talks into this seminar, that 3D printing is good for design for freedom. We can print many designs based on the 3D model. It deposits the material where there is a need of material. So due to that reason, you can see an example of 3D printed concrete sample by Xtree. It is a coral reef. So what is the purpose? They wanted to bring this kind of very complicated structure to attract or to grow coral reefs into a marine environment. This kind of structure making by casting is really a complicated task, and it needs lot of labor work, and also it is expensive to make this casting molds. In this regard, the team, they came up with a new technology, that is the 3D printing of concrete. So they made a special concrete that can be 3D printed layer by layer, and with the help of that, they have come up with this kind of complicated design that is used as a coral reef. So design freedom is the first aspect that leads to the designers, architects, your builders to think of a new technology that can help them to create such complicated geometry with a very low cost compared to casting. Second reason, which is very close to my heart, is all about sustainability. Normally, when you talk about manufacturing, nowadays everyone is talking about sustainability. we are not only responsible to create material, but also nowadays we are also responsible to make a sustainable way of using the materials. In many countries, when I was in Netherlands few years back, when one day I was traveling to a company, and I came up a very nice tagline that these days we are not here to only generate new materials, we are also responsible to use them more efficiently to bring more sustainable materials into our world. So sustainability topic is very close to my heart, and in this regard, especially in the civil sciences, there are so many new materials that is created in the more sustainable way by including some industry waste material or some kind of plastic waste that has been incorporated in the concrete materials to make it more sustainable. But what is here with the 3D printing of concrete that is even much more interesting? There's an example in the picture. You can see this is a 3D printed bridge, entirely 3D printed bridge in the Netherlands. And if you see the cross section of the bridge, it is not entirely solid, rather it is topologically optimized. What does it mean? That now we have the design freedom, and using that we can always optimize the material distribution given in a structure. And it is possible to fabricate such kind of complicated structures because we are having a 3D printing machine which can deposit the material where there is a need of material. So it means now the structures we are going to print, the structures we are going to make for any applications can be even more sustainable because we can print them in a much more accurate way, and we can deposit the material as per the loading condition. So these two reasons are there for me to accept this technology for building and construction applications. Apart from that, there are many other reasons, like if you bring a 3D printer, the task can be completed in less time. There will be no or very less labor involvement for creating the buildings. With these regards, we started our research in 2015, and this is the graph of state of the art of concrete printing technology. You can see the technology actually started in the year of 2005 or even before that. But in the year of 2010, when a Chinese company called Winson, they started printing lot of buildings, houses using this technology, then concrete printing getting lot of attention from university, academia, researchers. And as you can see, in 2015, when I started my PhD at Singapore, lot of companies, university already were in the field to adopt the technology. Recently, when I was going through an article by World Economic Forum, normally they post many articles regarding the future of constructions, future of manufacturing. So this article was very interesting to me, and I came to know that, I came to know that they wanted to create a new, the future of constructions in a more construction 4.0 way, which includes not only a very high-end manufacturing process, but also they want to connect internet services, IoT devices together with the machines so that all the activities can be tracked, they can be optimized, and they can be scheduled for more productivity. So this is their plan, for which many companies are working together to make the future of constructions more automated, more digitalized, and they also want to bring more connectivity in the process planning so that a construction, a contractor can track all the activities, and as the result of that, they have to minimize, they can minimize the cost of the entire building products. They can also minimize the waste. And also recently, due to the development of more automated construction processes, you can see I was going through an article in the newspaper published few months back that in the Japan, during the COVID times, they wanted to create a dam, and due to the lack of human resources, they wanted to use some kind of construction robots which were at the very early phases. And they reported that using those kind of construction robots that can put the concrete, that can lift the mold, that can join the rebars, they were able to improve the productivity time over 30%. And as a result of that, they were able to save the cost up to 40% by utilizing those robotic automated machines. So this is an example of 3D concrete printing that we developed at Singapore. So this is a machine like your FDM. You might know the fused deposition modeling, where the molten plastic used to be deposited layer by layer. So similarly, we made a new machine because when I started my PhD, that time no commercial vendors were available for supplying these machines. So we made our new 3D printing machine to deposit cement-based composites. So if I talk about the process pipeline, it is almost similar to the fused deposition modeling process, where you extrude the concrete or the fresh cement based mixed layer by layer directly from a 3D model. So first you create the 3D design, you slice it according to the layer thickness, and then you put the G code path planning, and then the machine is going to print the entire structure for you. So here you can see the only difference is that since we are talking about large scale printing, the layer thickness are quite unusual here. If you remember, or if you have ever used FDM 3D printing process, the normally the layer thickness is some millimeter, 0.2, 0.2, 0.6, it can go up to max 1 millimeter. But in concrete printing, our layer thickness is quite thick. We are printing layers up to 30 to 40 millimeter thickness, and the width can go up to 40 millimeter. So in this example, I think you can see that a rotating nozzle is depositing the material layer by layer. It is a very fresh material. It can harden immediately, or it can even stay fresh for a few hours without any hardening. These two kind of materials are possible for these applications. So the unique thing is that here you can observe the nozzle is rotating. Why it is important? So when we started making such kind of machine, we observed that if the layers are not circular and you want to print rectangular or square filaments, you have to create a rotating nozzle so that the rotation motion should be always tangent to the path. Otherwise, the layers are going to be twisted. And due to that, so we modified the machine planning in such a way that if you are using a rectangle or square nozzle, the nozzle can rotate so that the path will be always tangent to the line. And therefore, you can see the layers are completely deposited uniformly without any discontinuity. So this is the entire machine we made in the lab. We called 4-axis gantry printer. The frame looks like a gantry frame, and it's a 4-axis because you can see there are 3 main axes, X, Y, Z. The 4th axis is not only it's actually your nozzle that is rotating during the motion. On the left hand side, you can see the control box. So when you are writing any code, you dump it to the controller sends the command to the machine, and the machine deposits the material layer by layer. So this is a large scale 3D printer. You can print the structures up to 1.2 meter tall. Also in the same direction, length and width, you can go up to maximum 1.2 meter. On the bottom corner, you can see I have attached a pump picture. So this pump is used to feed the materials to the nozzle. We normally call this is the extruder. The tip is nozzle. So the pump is connected to the extruder with a pipe, and through which the material will travel to the point, and then you can deposit the material layer by layer. So now this is the complete, even the same thing can be done with the help of a robotic system. I will show you one interesting video that where robots are being deployed to do the same job. But in the lab scale, we started first with this kind of gantry printer because it was very easy to program it compared to a robotic system. So now if I see the system, I divide the research avenue into 3 domains. One is the material domains. Second is the automation, where you can create much more complicated machines for such applications. Third is the structure. What structures you are going to print, how you can optimize that. Have you done any kind of optimization course? And if it is so, can we apply those things to this unique machine which can print this kind of optimized shape? So these 3 research avenue are there for a concrete printing topic. So we started working one by one. So today I am going to present our research findings in these 3 domains. I will try to make it more simple so that you can easily understand the concepts. And in between, if you have any doubts, please free to ask me. So the first challenges is the material development. Let us imagine a case you want to extrude a material using this 3D printer. So during extrusion, it is very important. Once you extrude, the material should able to retain its shape edge of your nozzle. Suppose you are printing with a circular nozzle, the material that is extruding, the filament should retain its shape. It must be in the circular shape. If you are printing with a rectangular nozzle, the material or the filament after extrusion should maintain its shape according to the nozzle. And when we are always mapping with the nozzle area, we call a factor called SRF, that is called shape retention factor. It is nothing but the area of the filament divided by the area of your nozzle. So if your filament that is extruding is perfectly in line with your nozzle area, you will get as SRF of 1. If it is not, then you will get low SRF. So what are the challenges in extruding such kind of material? Forget about the material. Let us imagine you have a soft jelly-like material. You want to print it for 3D printing application. So during printing, it is very important that when you are extruding this material, it must retain its shape. So when we want to retain the shape, the material must have high viscosity or high yield stress. Otherwise, you can't make sure the material will retain its shape. If we want to make the material low viscosity or low yield stress, what is going to happen? You are going to end up with something which has been shown in this picture. After extrusion, the material will spread away on the build platform. You are not able to retain good shape compared to the nozzle area. So this is the case of extremely low viscosity. If you want to extrude a very high viscosity material, what is going to happen? During extrusions, the materials may not be continuous. As you can see, we may end up with such situation where discontinuity will happen. So it means that we have to properly develop a material which can be extruded smoothly, and after extrusion, the filament will retain its shape. So normally in the concrete science, we call it a contradicting property, because you imagine a situation where the material have to flow from an extruder, so it have to be very low viscosity. If you want to make an high viscosity material, you can't extrude from the nozzle easily. It have to be low viscosity, then only it will come easily from out your nozzle. But if you want to extrude that same material having low viscosity, you will have a situation like shown in the first figure. So the contradicting challenges are here that we need a material which is low viscosity during extrusion, and once you extrude, the material must have high viscosity. How it is possible to create such a material which during extrusion will possess low viscosity, but as soon as you deposit on the print bed, it is going to possess viscosity, because we need a better shape retention. So in this regard, we have to come up with some kind of calculations to find a printability window where the yield stress and viscosity are perfectly matched, so that it will be extruded out smoothly from the nozzle, and once it is deposited on the print bed, it is going to retain the shape. It is possible by a concept known as thixotropy. Okay, so those who are from fluid mechanics background, I hope they can understand the concept very well. Thixotropy is nothing but it's a phenomena that we see many examples of thixotropy in our day-to-day life. Imagine a situation in the early morning when we want to squeeze the paste. Okay, so when you squeeze the tube, the paste comes out of the tube very easily, and you can see it remains stable on the brush itself without any deformation. And as soon as you stop squeezing, no paste comes out of the tube, it remains in its same position. If you squeeze, it comes out easily. If you stop squeezing, it remains in its own position. So we need a similar material for extrusion based 3D printing because we want to have such material that can be extruded easily, but after extrusion, it should remain its shape without any deformation. And this is because of exotropy. If I further simplify, I can call that this material behaves like a shear thinning material when you apply some force. If I'm squeezing it, I'm applying some force due to which the material is having shear thinning property. And due to the shear thinning, the viscosity goes down and it can easily extrude out from the tube. But as soon as I stop squeezing, as soon as I stop applying any force, then this material is not having low viscosity property, rather it is having its original viscosity, due to which it is remaining in its own position without any deformation. And to do achieve such kind of thixotropy property in the cement composites, we have to play with lot of material composition. Suppose we are using sand particles as in composite materials, so we have to properly take care of the particle size. We have to also consider how much water we are adding into the system. All these things are very important, including your binding system, which is cement. So cement is a glue for concrete engineers because they want to make a glue by adding water to the cement, and then with the cement glue they want to hold all the sand, rocks to create a concrete block. So this is how this material has been made. So if you want to have such kind of thixotropy property in the material, it is very important that you have to expertise in the material characterization, and you have to properly optimize the sand gradings, the cement paste formulation, the water you are adding. Everything have to be optimized in such a way that these things can be improved for thixotropy characterization. So you can see a graph here that if you want to have different particles of different size in your mix, how the viscosity are going to change. If you want to create your own 3D printer, you have to make your own material. So when you want to make your own materials, the particle size in the materials are very important. And in this regard, you can refer such kind of graphs where it tells you that in the material, if you have different particle size, different composition, the viscosity of the materials are significantly going to be changed. And therefore, if you want to have a best material for 3D printing, you need to optimize all these combinations so that the proper viscosity can be obtained for 3D printing application. So just now I mentioned about that in the cement science, the most important point is the glue. The glue is the important point because ultimately it's going to bind the rock, sand, all these things. So when the cement is very important, at the same time we see that cement production is a energy intensive process because everyone knows that it produces or it emits lot of CO2 into the atmosphere during its production phase. So what we wanted to have, we want to make more sustainable material by including some kind of waste fly ash. So this is the fly ash from a factory in India. So we wanted to put this kind of fly ash and we want to make a new material so that the materials will be more sustainable. And if you see this waste fly ash in the microscope, you will see they are more sphericals, okay, round shape. As you can see in the right hand pictures, they are more spherical in nature. And then when we added this kind of spherical particles into our mix, they acted like a ball bearing elements. So they have the tendency to flow easily during your printing. So ultimately you can imagine what will be the consequence. So when we have a material which consists of spherical particles and they simply want to have a ball bearing effect, it means if I add little bit of extra water, this ball spherical shape kind of particles, they want to always flow away. So with such kind of material development, you can imagine that after printing a few layers, the whole structure is going to be collapsed. Okay, you can see easily that I printed using the waste fly ash, and after printing up 3 or 4 layers, the complete structure has been collapsed. And one important point I would like to highlight here, that unlike other 3D printing, you take polymer, you take ceramic, you take metals, any material you take, you will see that once you deposit the material, it will immediately harden Otherwise, you can't deposit more layers. But concrete printing is such a new process where you can print at least a structure of height 1 meter without hardening the bottom layer. What does it mean? It means that even the structures are not hardened, I can still print a component of height of 1 meter without hardening the bottom layers. I can still put my fingers and take away some materials even if you have printed a 1 meter tall structure. So that is possible because of texturotropy, because this texturotropy significantly has higher viscosity which holds all the layers before it. And it is possible only in concrete printing, but nowadays there are a lot of advancement has been done, so we can print the material, and once you deposit on the print bed it can be rapidly hardened. It is important when you want to print something beyond 1 meter. Normally in the China, when they printed the entire buildings which is consist of more than 500 or 1000 layers, you can't print it without hardening the bottom layers. So if you want to print some small structures, maybe up to 1 meter tall height, then you can easily use this material. It won't be any problem. But in case you want to print the entire building, it is possible. I will show some examples. We have done it here. You have to rapidly harden the bottom layer. Without that, it is not possible to print up to 3 meter or 4 meter tall structure. So what we did here, since we wanted to have a sustainable materials, we added some kind of nanoparticles. These days, nanoparticles are doing amazing jobs. And in this regard, what we did, we took some nanoclay and just added 0.5% of the nanoclay to the cement that we have used in our mix. And we found that just by adding a very small portion of the nanoclay, the yield stress or the viscosity you may consider, it significantly improved up to 5 times compared to the mix we have printed in the earlier slide. So now we have a mix which is having more or higher viscosity than the base mix, and we expect to print more layers without any failure. Now the question comes, when we are improving the viscosity, does not it going to affect the extrudability? Because when you are working with an FDM kind of printer or any extrusion based 3D printing process, 3 things are important to you. First, the material design, the machine design, and once you have machine and material, 3 things you have to work upon. One is your extrudability test. You have to make sure your material is extrudable. Then buildability test. You have to make sure you are able to deposit many layers without any deformation in the layer. And third thing is that time. So how much time it takes to harden the complete materials, because it is important when you want to do a large scale printing. Without this idea of hardening time, you cannot make a plan of printing large scale structure. 3 things are important. First, to go with the material design and machine, and once you have these 2 things together, you try to explore extrudability of the material. If it is not extrudable, then you try to tune it by adjusting the particle size, particle packing density, so that you will pass in the extrudability test. Now you are able to extrude the material layer by layer, but you are not able to deposit 3 layers, 4 layers. After 5th layer, the structure is going to collapse. Now you have to work upon buildability aspect. How I can print more layers without any deformation. In this regard, there can be many strategy. So what you can do, you can print the material and quickly harden the entire structure so that more materials can be deposited. And once you have this kind of extrudability and buildability, the time, hardening time is very important, because it is going to tell that number of layers you are going to deposit. So in this regard, what we did, we tried to improve the viscosity, because our earlier mix was not having sufficient viscosity to hold more than 10 layers. Now we increase the viscosity so that we expect the materials can be printable more than 10 layers without any deformation. The point is, in this regard, if we keep simply increasing the viscosity at a point, we will not be able to extrude the material because of high viscosity. You have seen our printing system. Suppose we want to print 100 layers. So does it mean that I have to make a material having 10,000 times yield stress in the base material. It is not so, because we can't simply increase the viscosity just for printing more number of layers. Why? Because the machine is having some restrictions beyond certain yield stress or viscosity. It is not able to extrude the mix. Therefore, we have to put a bar at some point so that our material is extrudable without any problem. So we try to improve the yield stress always within certain limit. We don't cross the limit, because if you cross the limit, then it is going to be discontinued during printing. You will not get continuous filament. Your filament will be discontinuous. So therefore, we wanted to always improve the yield stress at our best so that it won't cross that limit. And even if you have a higher viscosity, you can print it effectively. And we did some little bit of research regarding when you added the clay, how you have to add the clay. Are you simply dumping the clay into the mix, or you are going to mix with the water, dump into the mix, or during printing you want to throw the clay onto the surface of the filament? There are different way to add the clay. So we also did some research on that direction, that even if you want to add some extra material into the base mix, what are the possible way to add it? We found that there are n number of way to add the clay into the mix, but in different way the clay is going to act differently. So what are the possible reasons? Capillary suction, hydration, water absorptions, particle packing, flocculation. So these are the few possible reasons by which the clay can affect the material rheology. So rheology is another keyword when you want to deal with extrusion based 3D printing, because always you have to optimize the rheology of your material for such application. For 3D printing of concrete or any printing of 3D printing, considering the extrusion mechanism, we want the flocculation to happen, because flocculation is the key here. Without flocculation, we can't print the material. So now what is flocculation? Let us understand the term, what I mean by the term called flocculation. You might have seen some example that in the rural area of India, so when we want to use the muddy water for some application, we have some kind of material. So by dissolving that, all the mud particles will settle down. So here what happens, by adding some chemical agent, the mud particles started to flocculate together. They start to make one group, and then they becoming heavy and they settle down. So similarly, in the similar line, the flocculation mechanism works in 3D printing is this. So when we have some particle in our mix system and you are extruding it, we do not need flocculation, because if the flocculation occurs, then you can't print it, because they're going to make big flocks, and the extruding such kind of flocks in the material are very difficult. Flocks means, just imagine some tiny particles, they're coming together, they are making a bigger particle. So extruding bigger particles is definitely difficult. So we do not need flocculation during extrusion. When we need it, we need it after you deposit on the print bed, because there, if flocculation happens, we can improve the yield stress. And there is a literature, there is a reason for that. This flocculation, it improves the viscosity or yield stress of your mix. And it really happened in case of nanoclay, that due to flocculation, this improvement was possible. And one more interesting point regarding flocculation is that in cement science, the flocculation can be broken down easily. Suppose these particles are accumulated together, they made a bigger block. You can apply some shear force to destroy that flocculation. So how it is related to 3D printing? Let me explain in a very brief line. So what happens? You make a material with a higher degree of flocculation capability. So during pumping or during extrusion, when the screw inside the machine is going to extrude the material, it is going to apply some shear force, and it is going to destroy the flocculation capability, so that the material can comes out of your nozzle very smoothly. But once it is deposited on the print bed, there is no external force acting on it. So again, this material will flocculate and it will increase the yield stress or viscosity and enable you to put more layers. So this is the key signs of extrusion based 3D printing, that you make a flocculated material, you pass through the nozzle. When it is passing through the nozzle, it is being applied through a shear force, and this shear force will destroy the flocculation. It will lose its viscosity. It will come out of the nozzle very easily. And once you deposit on the print bed, again flocculation will come into the picture. It will increase the viscosity, enabling you to add more layers. So these things happened in our case. So you can see the nanoparticles in that microscopic view. Okay, so the flocculation, as I mentioned, it is going to improve the yield stress and viscosity. So this is the schematically things that just now I explained, that at rest they are making the flocculation. So when you are extruding it, this is not possible. So they are getting destroyed. So they are in getting in line with your force. And again, once you deposit, they are coming together. They're making the groups flocks, and due to which you are depositing more layers. So this is how the 3D printing process works, by flocculation mechanism. And as I mentioned, with such kind of new materials, you can print more layers without any deformation. So this is all about material development. But like during printing of such kind of materials, we observe a very minute deformation of the layer. So when such deformation keep on continuing for 100 layers, ultimately there is a chance of complete collapse of your structure. So we therefore define the deformation into two divisions. One is elastic deformation. During printing, such kind of small deformation will occur. At the end, it may lead to complete deformation of the entire structure, or you may experience some kind of plastic collapse during printing. Your material is very stiff, you are able to print 10, 20, 30 layers. Suddenly the bottom layer strength will fail down, and it will destroy the complete structure. So two kind of collapsing can be possible, and to track it, we have done some work on the machine design. Okay, I told you from the very beginning that three avenues are possible. One, you try to involve yourself in the material explorations. You keep on developing new materials by adding some nanoparticles. Second way is that you try to improve the machine features. Nowadays there are so many new machines coming into the market with lot of sensing features. So in the similar line, what we did, we tried to attach one kind of sensors to our printing system, so that during printing we were able to track the layer motion, how the layers are being deposited. If there is any kind of deformation, that can be also tracked from the sensing unit. Why it is important to do so? It is important because we want to develop a machine learning model, and this machine learning model can further help us to automatically set the parameters in such a way that I will not see any deformation during my printing process. Nowadays, like due to the that industry 4.0, everyone is trying to connect the data with the machine. So therefore, in this regard, we thought, we have the machine, let us put some sensor for some applications, get the data, build the model, and now this machine learning model, or using some artificial intelligence, we can make a better model. I will show it in the next slide, that how this model is able to help us to improve the buildability. Now we don't have to rely on the human intelligence. We are rather collecting many data points from the process with the sensing facility, and then with the help of machine learning, we made a model, and this model is going to now tell you where to improve and how to improve it. So this is some examples that with the new materials, we always try to improve the buildability. I told you three things. Once you pass in the extrudability test, you have to work for buildability. So at the initial level, we were able to extrude the materials very good, and then we try to improve the buildability in terms of number of layers. So every day we are doing some experiment to improve the buildability, and always we do some kind of material study in terms of microstructure strength, so that this material can be further used for some application. So now I'm going to tell about a very unique material development that was I was involved in the 3D printing of polymer material. It's called geopolymer. So we actually work upon this material for a specific competition. I forgot to tell you one thing: the evolution of this technology. Usually what happened? I think in the around 30-40 years back, um, Professor Koshnabis from a university of US university, he proposed this kind of robotic printing of concrete structures for astronauts who are traveling for some space exploration. He proposed and patented the technology that one day this kind of automated machine will go to space. It will create the habitat for the astronauts by depositing the material layer by layer. It will make some kind of spherical dome for the astronauts for their space mission. And then what happened? After a few years, some Chinese company and some university, they worked together. They work together to optimize the process for printing houses, buildings in the earth. And therefore, this technology came into the building and construction domain where they wanted to print some kind of building structures. But the origin was to print this kind of habitat in the space for the astronauts. And in that line, the NASA, they organized one competition. They wanted to print some material in the space atmosphere, and the condition was that you develop a material in which we need a very less amount of water. So with that competition in the mind, we developed some kind of geopolymer material which was activated by the chemical composition, not by the water. So you can see that we again use some kind of waste materials. Here instead of water, we use some liquid potassium silicate activator to optimize the mix design. And you can see that what is the beauty of this process, that when you have a different materials, always we try to explore what are the key components that is affecting the rheology. I told you the keyword rheology. So when you are dealing with such kind of extrusion based 3D printing, rheology is the key. So we always try to find what are the key raw materials that are affecting the rheology significantly. So here you can see in the example that we started exploring that the activator that we are using, is it really affecting the rheology or not? In that regard, the activators that we bought are available in different concentration, or you may call molar ratio. And we try to see if tomorrow we change the molar ratio for some application, is it going to affect the rheology? And in this regard, you can see that in the picture I have two molar ratio 1.8 and 2.0, how they are affecting the yield stress and viscosity. Okay, so what is going to happen if these two chemicals having two different molar ratio 1.8 and 2.0, they are having different viscosity, and you'll be surprised that this viscosity is higher than the viscosity of the water. So it means previously I was using a materials with water. Now I'm using an activator which is having higher viscosity than the water. So ultimately, by using this activator, I am going to end up with a situation where my material is going to be more viscous, because previously I was using water which is having viscosity of 1 in the unit of MPS, but now I am having an activator of different concentration, and it is seen that in any concentration 1.82 or beyond that, its viscosity is increasing. So now when the activator viscosity is increasing, what is going to happen? It is going to increase the viscosity of my material. So here an example, you can see that when I'm using the material with the activator of concentration 2.0, I'm getting SRF of 0.92. If you remember my first slide, you'll remember that the SRF was only 0.34. Okay, now due to the improvement in the viscosity of the activator, I am getting more viscous liquid within the prescribed limit, and then as a result of that, I am getting a very good SRF, that is called a safe retention factor of 0.92, and you can see that how the layers are smoothly deposited without any discontinuity. But in case of 1.8, since the viscosity is low, I am again getting the similar SRF, which is around 0.34. But in practical, if I go for some application, 1.8 is going to give us better strength. compared to 2.0. Okay, so in that regard, what we did, we again make our own nanoclay to improve the poor performance of 1.8 molar ratio activator. So you can see that during printing also, if you have a poor material, after printing up 3 and 4 layers, you will see this kind of deformation of the layers. Okay, so first you can see that from the nozzle tip to the first layer, with printing time, some gap will be generating throughout the printing process. It means your material is deforming and the layer height is increasing. So this is the experience you will find, that when you are having a poor material, it means after printing of 3 and 4 layers, this distance is going to increase sharply and the whole structure is going to collapse. Usually the program was made in such a way that this distance will be always remain 0. And why this distance is coming into the picture? It is because that your material is slumping, it is deforming during the process of printing, and the result of that, you are getting some deformation in the print height. Okay, but if you see that improved material that we designed for such applications, it don't have any kind of distance between the nozzle tip to the first printing layer. So it means this material is not deforming and it is very stiff. We can deposit more layer without any further deformation. So now coming to the material characterization, this is the last slide from the material perspective, that when we always deal with the materials, it is very important to do thixotropy characterization. I already explained the thixotropy signs. So it means you can see that when you have a material, in the beginning you have high viscosity. It was more flocculated state. Now this is before extrusion. During extrusion, what happens? It is the middle region. So in the middle region, you can see the viscosity almost very zero, almost like around 1. So you can't see it. But once you deposit on the print bed, again the material has the capability to recover its original viscosity due to flocculation region, and due to that you were able to deposit more layers without any deformation. So with this material, we try to print some kind of small structures to showcase the material capability. And this is the final video we sent to them, because they wanted to print the material not only not by using a gantry system, but using a robotic system. So we made some programming using a small scale robotic system, and you can see the video here, that how we wanted to print the structure for the habitat using a robotic system. Yeah, so this is how we have printed the entire structure. And other possible designs also, we try to print it using this robotic system. So you can see that even some complicated structures are also possible to print out. And now we thought that we are enough matured to bring the technology for the construction industry, for which we really work upon in the initial phase. So we wanted to print some kind of low cost housing, because we know that technology does not cost much, but if we want to bring some sustainable materials, it is possible to take this technology to the market. And in this regard, so we wanted to further extend the technology for large scale printing. So I told you very beginning that when you want to do large scale printing, it is very important to harden the materials immediately, because without hardening the bottom layer, we can't print 5 to 600 layers. So it is possible that we can do some material tuning in the nozzle itself, so that after we print or after we deposit the material, it is going to harden rapidly. So here is a schematic of a process, that what we do during printing, we have an extruder. Here we add some kind of chemical activators or accelerators that is going to harden your material immediately. So here is an example. You can see that once you deposit some material, some chemicals, it is going to immediately harden the material. So the complete picture, you can see it here, that this is the robotic system. We have been two inlets, one from the material, another for the chemicals that is going to be mixed and deposited, so that once you deposit the material, immediately it is going to be hardened. Okay. And also in this regard, we can print many layers without any issue. But the point is, when you are having such kind of rapid hardening material, it is very important to characterize how it is going to deform. So we did some strength test. You can see here example that the materials are being compressed using a compression machine at a different time interval. Time is very important in concrete printing, because for example, we are using a mix. Now we are printing it. After 20 minutes, if it is getting hardened, we are not able to print it, because it is not going to pass through the extruder. And therefore, we have to always print fresh material. But with time, it is going to harden on the print board. So when it is going to harden on the print board, it is important to know how it is going to fail and how fast we can harden it. And in that regard, we did some green strength test. As you can see in this picture, we wanted to know at which time the material is going to fail, and we show that we can accordingly add the accelerator into the mix to avoid any failure. So we did some this strength test, and also we conducted some shear test. And with the data obtained from these two tests, we tried to build a model. So I'll show, this is the model. So you can see that this model is used to predict the failure. So now I told you from the very beginning that when we have a lot of data points, it is possible to create a model. And this model is now going to tell us for an unknown material with some, if you input some viscosity, yield stress, particle packing density, it is going to predict when the structure is going to collapse. So therefore, it is very important to do the modeling for large scale application, because in any worst condition, if it is going to collapse, the materials cannot be reused. Why? Because we are using a rapid hardening mix. If it is collapsing, if by any reason, we can't use the material. Therefore, it is important to always understand the process from the very scientific point of view, so that during deposition, it won't able to have any kind of small deformation, which is going to lead to the complete collapse of the structure. So this was the complete story for development, machine design. Now the key things comes into the picture, because in every 3D printing, we have some process parameters like printing speed, layer height, nozzle height. All these things are significantly going to affect your properties of the part that you are printing in the machine. So here I can schematically showing here that process parameters is the first important point, then materials, then design, and if you want to do some post processing, that also being taken care for optimizing the part properties. So if I want to explain the process parameter effect, you can see that here, if you want to extrude the material layer by layer, okay, so now it is important to know what is the print speed you want to maintain. So in this regard, what we have done, we have kept the pump flow constant, and then we change the print speed. And always we wanted to check that what is the optimum print speed for which the filament width will be equal to the nozzle width. So we came to know that keeping the flow rate constant, if we print with 80 millimeter per second speed, the width of the filament is same as the nozzle width. So in that regard, the shape is remaining same. So therefore, we always print with 80 millimeter per second speed because the width of the filament will be similar to the nozzle width. If you print faster, the width will be smaller. If you print slower, the width will be more. Regarding the nozzle shape, I told you from the very beginning that if I want to use rectangle or square nozzle, we have to rotate it. But in case of circular nozzle, in case you don't want to rotate the nozzle, it is possible to print it. So you can see that. But in case of circular nozzle, we may have some kind of macro pores, which is going to significantly affect the mechanical property of the part. Therefore, it is important or suggested that you use some kind of other nozzle than the spherical one, which is be going to give more compacted microstructure. In the bottom pictures are shown that in case of having a nozzle with different shape like rectangle, square, how we are going to get a complete dense microstructure. So with those understanding about the process, material, design, we try to print a very small toilet unit which is having 1.2 meter tall. And you can see this is the design. And during the design phase, we found that design of the structure is much more important in 3D printing. You might have heard the concept for design for additive manufacturing. So here, the design for concrete printing is important because we came to a conclusion that if you have a sharp corner and you are not having a proper material, then you are going to end up with such kind of sharp tears. You can see these layers have been teared and some surface cracks were observed. And it's because that this radius of curvature was too small for the developed material. So in this regard, either you increase the radius of curvature, you can see that from 40 to 100 or 80, we have increased the radius of curvature only for this component, and this sharp tear was nullified. This effect was not noticed. This is one possible way to omit this kind of defects, or you make more soft materials, or print speed you maintain it to low range. If you travel very fast with a very stiff materials with a very sharp corner, you are going to get this kind of sharp tears. To avoid that, either you increase the radius of curvature or you print slowly using a softer material. So what is the key conclusion from this kind of study? That in 3D printing, your design, material, process parameter all are related. You can't simply just optimize one factor keeping the other variables constant. So all three are having their own dominating role in the printing process. And then when you print, it is very important to know the strength. Okay, like casting, we always get one strength, but in case of 3D printing, we have the layering issue. So in this regard, we always get different strength in different direction. To quantify the strength, we printed the entire block and applied the force in 3 different direction. And surprisingly, you'll see that this is the printed block and we applied the force in 3 direction. We found that in 3 direction, the strengths are different. Okay, as you can see in the compressive strength chart, the first one corresponding to F1 direction, second one F2, and third is F3. C belongs to casted sample, and in F1 direction we got better strength than casting. F2 is also better. F3 is slightly almost similar to the casted sample or slightly less. Okay, there are some reasons. I don't want to explain it now, but I will show you some interesting case that when we did the 3-point bending test, there are 2 directions which are very interesting. This is F2 where the layers are perpendicular to the loading directions, and here is parallel. So now in case of F1 direction, we got very low bending strength. It's because that the bond between these layers were not strong. So when the bond between these layers are not so strong, in F1 directions, definitely you will get very poor performance. So now we got a concept of bond strength. And in 3D printing, it is very important to consider the bond strength between the layers. And in that regard, what we did, we printed different layers in different time interval and we conducted the bond test strength. We came to a conclusion that in 3D printing of this kind of cement-based composite material, the bond strength is the parameter of material, time gap, and process parameter. Because if you're printing a material having very quick setting time, in just 2 minutes, 3 minutes, it is going to completely harden. And in such case of printing material, if you delay 2 minutes in between the time gap, then the bond is going to be very poor. It's a very general observation. So that's why if you're printing with a very quick setting materials, it is advised that you should not delay the printing time between the layers, because otherwise you can see that the bond strength with respect to time gap is going to decrease, and it's because the material is rapidly hardening with time. So a further delay between the time gap is going to give you a poor bond strength. So in that regard, there are again some strategy to improve it. You can either optimize the material, you can optimize the design, or during printing, you can slightly press the material so that this kind of micropores, what you have seen in figure A, can be omitted. And in figure B, you can see that during pressing the layers, we can see that there is no this kind of micropores is not visible anymore, and there is substantial improvement in the bond strength by pressing the layers. So we have done many projects to understand the importance of material, machine design, as well as the process parameter. And with that knowledge, we started doing some kind of projects. You can see our first project was to print a modular toilet unit. And that time I was in Singapore. Our prime minister visited Singapore for some occasion, and we printed this entire toilet in front of him, so that in 60 minutes we completed the printing of entire toilet unit with the developed material. And he really appreciated the advantage of such technology for printing or bringing automation in the construction industry. The next project was to printed a complete prefab toilet unit for some buildings in Singapore. You can see on the behind that this is the big robotic arm we used for concrete printing. And with that, we were able to print the entire structure with our machine. So this is the entire 3D printed toilet unit. It's around, the height is around 3.2 meter tall. I have a video, you can see it, how the printing was done. And then you will get a realistic pictures of concrete printing process. So here it goes, you can see. Yeah, so you have seen that how that printing machines or the robotic system was used to printing this kind of walls, which is lattice wall. Normally we make this lattice walls to make the wall more lightweight. And whenever we are printing with cement material, everyone knows it's a brittle material, and therefore reinforcement is must. So we have some special nozzle to reinforce steel cables, fibers into the mix, and we have seen improved performance with our new mix design. The same robot was used to print some kind of curve structure, like non-planar printing is also a trendy topic in 3D printing. So we also did some research on printing non-planar structures. You can see the bed is not a flat bed, rather it is a curved bed. So we use the programming technology to print the structures on a non-planar way. Okay, and the application was for buildings. We use facade elements, and we intend to use such kind of non-planar surfaces for facade applications. So coming to the end of the talk, I want to highlight the importance of this technology. There are many companies in outside India. They have started exploring this technology. This is a machine from Saibi, Netherlands. They are printing the entire office in Dubai using the robotic 3D printing system. So you can see another company, Xtree. They were expertise in printing very complicated structures. This is a big nozzle. It is actually mixing the chemicals and making the material quick set, so that once you deposit in 2 or 3 minutes, it's going to harden. And you can see that level of complexity they have achieved during printing. So recently they have printed the storm water collection unit, the rainwater collection unit. So they feel that by casting it takes a lot of time, and by printing they can minimize the fabrication time, and as well as they can make it more lightweight. This is a large scale structure they have printed for such application. Another company, Basics 3D, they are also pioneer in printing very complicated structures, which is really expensive to make by casting, because you need to really make a negative mold in this way to make such kind of complicated shape. Hmm. They're also using robotic system. They are also good in making some kind of urban furnitures like benches, tables, using the new materials. You can see in the some park they are able to print some kind of furnitures, so that they are trying to sell it to Dubai government. This is a company called Episcore. They have printed the entire building in 24 hours. They have a crane type of system. So you can see they have made a small house using the crane system. They are depositing the material. This is the interior of the building. It has been printed. The same company now they're exploring. Actually, this is a Russian company. I wrongly put it Netherlands. So this is a Russian company. They are trying to print the entire building in Dubai for some grant. So you can see that in a desert, they are using their 3D printers to print the entire building, and the walls are like lattice wall. They want to make it lattice wall for lightweighting applications. The plumbing, the electricity pipe can be go inside it, and this is the complete building after 3D printing. So it is really possible to print entire building. In China, they have printed the 2-story building. So what they have done, they have printed the walls and assembled it on site. There are so many examples where you can see Chinese company, they are printing the buildings. Again, the same lattice wall design has been used for many applications because it's easy to print. During COVID days, they also printed many cubicles because they feel that bringing the construction workers to the field, doing the casting, curing, a lot of time it takes. And for printing, since the material is quickly, rapidly hardening, it is easy to print by design. So they adapted the technology to make such kind of cubicles. And already I have shown this breeze to you that many companies, they are now trying to make some kind of real scale examples with 3D printing. So now it is not in the research phase, rather than it has been adopted in many examples in the building and construction industry. So as I show you, the topology has been optimized for some loading applications. Recently, the same company, they have printed the complete staircase for a metro project because they feel that bringing laborers, casting it takes a lot of time. So to minimize the time, to minimize the cost, they printed the entire staircase for such application. In IIT Guwahati also, we have a 3D printer. So we have started making many structures. So you can see this is our first work, and soon we are going to have a large scale printer for printing low cost housing solutions. So far, we have no idea about the cost because there are so many unknown variables that is being affecting, but slowly we're exploring these options. The key takeaways from my talk is the entropy is the key if you want to work in this domain. Material, machines, design are all interrelated. And of course, when you're talking about a brittle metal printing, reinforcement, structural integrity is the key questions. And now when you are having such a new machines, it is important to come up with some new method of testing, because sometimes we feel that the existing test method is not suitable. And last point, what I mentioned, that so far there are so many unknown variables, we are not able to properly find a economic calculating point so that to make it more cost affordable. So in this way, I would like to thank the organizer for inviting me to give this opportunity to talk about this new technology. Hope you like it. If you have any questions, I'll be happy to answer it. Once again, thanking all of you for attending this seminar.
Thank you very much, sir. So participants, you can ask the questions. You may type your question in the chat box. So there is one question, sir, in a chat box you can refer to. Question by Mr. Sachin O. What is the life cycle duration of 3D printed concrete part?
Okay, it's yeah. Thanks for the question. It is a really good question. Normally, we have not done such kind of testing. The bathroom unit that you have seen in that robotic 3D printing, actually what we did it for application, we gone for some testing, almost like 30 to 40 testing that was required by the building and construction team from Singapore, and we passed in all the tests. But regarding the total life cycle durability, this question still needs some research. Okay, at this point we are not too sure about the durability. There are some pilot projects being done in India also by IIT Madras and some other university. They are exploring these options that if someone want to adopt the technology for making low cost solution, is it really durable? And some structural testings are still ongoing. So at this point, it is difficult to answer this question. But just to answer your question, I can tell that research is ongoing on this topic. So if you have some other things, I'll update it in this matter.
Okay. Okay. Any other questions? Participants can unmute themselves and ask the question. Participant can discuss on any particular point. Just you can unmute yourself and ask the question, or you
And this
may type your question in the chat box.
and this technology is really getting a good attention from Indian investors, because recently we have some collaboration with JSW and other construction company. They are really interested to bring this technology to do some pilot project using some geopolymer concrete, because they found that geopolymer concrete is being adopted in many places in India. Of course, it is not popular like OPC, but they want to use some kind of novel materials. So I hope with the Indian construction team, our team at IIT Guwahati will do some good job for bringing low cost solutions to the Indian market. And maybe if the organizer organize some other conferences or short-term courses, will come up with some better new results, which we can do it for the development of India. With this, yeah, if you have any question, okay.
One more question in the chat box by Mr. KP Arun.
Hmm.
First of all, he has given a compliment for you. Thank you for the session, sir. Then he has mentioned, you have mentioned about the space 3D printing with concrete in beginning. My question is that with the zero printing, how will the concrete settle in the print bed, sir? Is there any research going on regarding this topic, sir?
No, it's a very nice question. It is general queries when I present such kind of space printing. Usually, I get this kind of comments. Okay, normally what we did, we have done some research on the anti-gravity effect on the material. So the point is, we have added some kind of nano fillers and some iron particles, and which really not only help in printing, but also in the anti-gravity environment. It is not setting as fast in atmosphere, but the setting time is quite long. So I have a paper in Nature Materials, you can refer it. So you can email also, I'll send you the complete paper, that how we have studied the anti-gravity effect on the concrete printing. Okay, so that paper is going to be published by Nature Materials. So we are already planned everything before we adopt this technology for the space applications. But unfortunately, without the clearance from some other agency, we have not disclosing it. But if you have any if you want to know more about it, you please feel to email me. I can send some reference results which can be helpful to you at this moment. Thank you.
Yes, sure. I will give the email ID to the participants so they can write to you on any specific queries they have. Uh, any recycle techniques, sir? This is the question by Kamala Kannan.
Yeah, recycling technique, for example, like normally we use recycled materials in our material development process. And also we wanted to use some kind of waste materials, because normally nowadays government is also pushing a lot of effort to make sustainable materials, sustainable structures. So we try to use more recycled products. Like recently one startup company, they were having some kind of plastic waste. So I asked my students to collect it from them and try to print it for your plastic printing. Normally we collect some kind of plastic garbage from the oceans, and then we wanted to use it either in concrete material, or I told them you try to make some kind of plastic that can be 3D printed. So this is possible in 3D printing. Lot of recycling materials are being used. There is enormous scope in this regard. You can work upon this material testing, characterization, how you will print it. As I mentioned, the key things, that extrudability, buildability, all things are important. So hope you will like it. Maybe if you continue your career in this regard, I can help you. So please do email me. If you have any further query, I'll be happy to support you in this regard.
Yeah, any more questions? Participants, please unmute yourself. You can ask the question. You may discuss if you want to discuss on any other point. I think there is no more questions, sir. Okay, surely if you
Sir,
have, yeah. Please
yeah,
go ahead,
yeah.
ma'am.
Good afternoon, sir. Such a wonderful session, sir. Nice
thank you.
examples you have given, complex 3D printing. Can you share your contact details or mail ID, sir?
Yeah, I think Dr. Kiran, please you share.
Okay, sir.
Yeah,
It is from
I will
Kiran, sir.
share,
Yeah, yeah.
I will
Okay,
share email
okay,
ID.
Kiran, sir. Yeah.
Yeah,
Thank
even,
you, sir.
I mean, all the email IDs of the speakers I will share, and if you have any specific question, you can ask to the speakers of this particular FDP. Okay.
Sure, yeah.
And tomorrow I will share all the contact details. I mean, particularly the email ID, and you can then discuss with the speakers. Okay.
Sure.
One more question, sir, in the chat box. While building bridges, we place steel beams inside the concrete. Can do the same in 3D printing, sir, or instead combine metal 3D printing with concrete 3D printing?
Yes, it is possible. You just type my Google Scholar profile. I have a paper where I combined metal 3D printing with concrete 3D printing. It is possible. I have done it. And also, like, it is not only the one way to combine metal 3D printing with concrete one, but in many applications, what we have doing right now, that we after a print, we are post adding the reinforcement. So we don't have to do metal printing because we did some cost analysis. Normally in Indian market, we always look for some costing. So we found that if we combine metal printing, it's going to be super expensive. Then we are not adopting that method, but from research point of view, we have done that. For practical cases, we are printing it only, and we are adding the reinforcement manually at this moment. But it can be also automated if some candidates are interested to automate. This is also possible, but this is the complete scenario. It can be done with metal printing, but it's super expensive at this moment. Rather, we are doing it manually. It can be done automatically if some provisions can be made. It is possible.
Yeah, thank you, sir. Any more questions from the participants? Participants may unmute themselves and ask the question. Okay, sir, I think there is no more question. So I thank you, sir. Over to you, the organizing team.
Yes, sir.
Yeah.
I'm glad to take this opportunity to give the summary and vote of thanks for the 11th session under this 3D printing and design FDP. I thank our eminent speaker for the session, Dr. Biranchi Panda sir, for his valuable time and deep insights on research avenues in 3D printing. Sir started by telling about the motivation behind working on cement-based 3D printing and gave insights regarding industries in relation with the same. Sir then shed light on the importance of automation in terms of digitalization in today's construction industry. Further, he answered the question why to print concrete and elaborated on various aspects of the answer like design freedom and sustainability. Sir then elaborated various other pros of using 3D printing and gave an in-depth overview on one of the case studies. Main motto was to connect the industry through digitalization technology. So further explained with the help of some examples like dam construction site in Japan, 3D concrete printing like fuse deposition modeling (FDM), 4-axis gantry printing. So then highlighted the challenges under the 3 research avenues, in which the foremost was material development. In the same lines, I shed light on texturotropy, material composition's importance in it, importance of viscosity in 3D printing, etc. Further, Sir shed light on cement production process, improvement in printability due to nanoclay, how clay affects rheology, importance of flocculation in the process, types of deformation in printing, which include elastic and plastic, mechanical properties of nanoclay, SF modeling mix. Going ahead, Sir explained about 3D printing of geopolymer, which was backed by engaging video demonstration. Sir then enlightened us about green strength stress. Further, to explain various process parameters, Sir talked about various projects which included 3D printed toilet units done in a day. Sir then shed light on reinforcement in 3D printing through curved bed 3D printing. Lastly, through examples of various companies like Saib Netherlands, XT France, Basics 3D, Sir explained the importance of this technology in today's world. We are grateful to you, sir, for today's very enthralling session. I'm certain that all the participants would reap great benefits from it. I thank all the participants for the enthusiasm and active participation throughout.
Thank you, sir. Thank you very much for being with us in this FDP. And thank you, Arundhati, for nicely concluding this nice summary you have made. So thank you very much. Thank you.
Yeah.
And for participants now, our next session will be at 5 p.m. by Dr. Vijay Bapat from IIT Bombay. So sir will be discussing on the product design aspects. So we will meet at 5 p.m. today for the third session. So the session will be 5 p.m. to 7 p.m. Okay, sir will be delivering his session from USA. That's why we have taken the time. I mean, the time is scheduled in the late afternoon. Okay, so hopefully hope you will enjoy the last session as well of the today's the series of lectures. So we'll meet you in the third session. Join before 10 minutes ahead of the scheduled time, so to avoid the last minute rush. Thank you very much. Have a nice lunch. Thank you. Yeah, participant, Mr. Santosh, you want to ask anything? Mr. Santosh Shekukar. Mr. Santosh Shekukar, you have raised a hand, so you want to ask anything?
Sir, yesterday I was present in last lecture, but I have not filled the feedback form of that session.
Okay, that feedback form will be available in WhatsApp. You can fill that, no issues.
Okay, sir. Thank you.
Okay, anything else? Yeah, Mr. Abhijit Patankar.
Yes, sir. Shall we join directly at 5 o'clock? No, after 2:30 session.
No. The third session is at 5 o'clock. Join just 10 minutes before, sir.
Okay, sir. Okay.
So that will be wonderful session, sir.
Sure, sure.
Vijay Bapat sir is very experienced. He was heading the department of IDC, IIT Bombay. And
Yes, sir.
Very renowned personality.
Yes, sir.
So
Surely.
join that session and get the benefit of the
Yes, sir.
benefits from the session. Okay.
Thank you.
Okay. Bye.